Hello everybody, my name is Luis Esser, and today we are here to learn how to perform species distribution modeling in R. I'm here with my RStudio open. I have R 4.6.0 installed, and we will be focusing on this package called caretSDM. This package is very nice for beginners because it allows to run every step of the workflow, SDM workflow, um, using only this package. You don't need to understand any other package in R to run a complete workflow for SDMs, okay? Uh, and it allows also for a lot of extensions, so it's a very nice package for advanced users. You can, as an example, perform new analysis on pseudoabsence generation or a new metric you want to try to use, or you want to create your own metrics. You can apply in a very easy fashion with this package. Okay, now let's start on how to download and obtain this package. The most straightforward way is to use the install packages function, which is native from R. You state caretSDM and it will download from the official repository. Yeah, but you can also download a more updated version from GitHub, and you do that by installing another package that is DevTools, Developers Tools, and this package has the install GitHub function, which you can download then a more updated version. It is actually 1.9.6. Okay, yes. And with the package installed, we can then open this package, and now we have all functions available for us to use. Okay, the first thing I want you to have in mind when you think about caretSDM is that it has three main ideas. Okay, the first is that we don't need to use any other package, so I will not be opening other packages here. I just use caretSDM. The second idea is that it has some key functions that other functions will orbitate. So we will have one object that we will create in the beginning of the process, and through our workflow we will be changing this object, and this object will hold information from the beginning to the end, and this will help us with our workflow. Yeah, so we have three main objects. I will write here three main objects. We have the occurrences object, which is created using the function occurrences SDM. We have the study area object, which is created with SDM area, and we have an input SDM object. Okay, so the idea here is we need two things to start our SDM approach, our species distribution modeling: the occurrences data, which will gather information about the species locations, okay, and our study area. And with these two objects together, we can unite them, and then we can work through many other processes such as pseudoabsence selection. We can perform our training, the predictions, everything together. Okay, now I will go through these three objects, and we will talk a little bit how to create each of them. Okay, and what sources we have to occurrences, what sources to predictors data, and with this information you'll be able to build your own objects and use your own data. Okay, I will try to focus on the main approaches, but I will use also I will try to show some differences that the package allows. Okay, so starting with occurrences. Usually occurrences are obtained in species distribution modeling through some database, and big database such as GBIF is, I believe, is the most used in studies, but you can also obtain data from field studies or from the literature. So I will show here 2 ways to obtain the occurrences object in caretSDM. The first one I already have here is with this function occurrences SDM. It will create an occurrences object which we'll be using in other steps. So the main idea here is not use other packages. So how would we do that? We need to import this data from our files. Okay, I already have some files here to help us. I put everything in this input data, and we have some predictors data, some study area, and our occurrences data as well. So I will be just writing here the directory in which the data is, input data, and then I will write the name of the file. And this alone, it's okay to run, but we have some information here that it's key to keep in mind when we are working with caretSDM, which is the use of the CRS. What is CRS? Is the coordinate reference system. When we are using occurrences data obtained from GPS or obtained from a database, these occurrences are always in some coordinate reference system. Sorry. In this case, the occurrence is in 4326, which is a main CRS. Like GBIF data is always in 4326, but you may need to use other kind of data that are in different CRSs. And the main idea here is that you don't need to focus on transforming this geographical data, because once we inform caretSDM that this occurrence data has a specific CRS, it will internally transform and make a lot of assertions and checks to make sure that everything is going according to the plan. Okay, so let's imagine that you have occurrences in one CRS and you have other occurrences that are in another CRS. When you try to put those two things together, they will not talk with each other. You need to have both in the same CRS, okay? You don't need to think about that in caretSDM. caretSDM, in the functions underlying the functions we are using, they will check for that. So this is the main way to enter occurrence data in caretSDM. I will write here OC, and I will show you that it will create an object that is from class occurrences, and it has a focal taxon, which is Araucária angustifolia, the Brazilian pine we are using here as an example. This data that was provided is a presence-only data. It has 419 records, and for those who are more familiar with simple feature data, it is here a print of the simple feature. Okay, so it has like a bounding box, has CRS, it's points, and so on and so on. Okay, now this is the main way that most people will enter occurrences into R from a local database, but you can also obtain, and I'll enumerate here differently. You can also obtain data directly from GBIF. This is, as I mentioned before, I will only use functions from caretSDM. Okay, so I will use this function that is GBIF data. I will put here Araucária, Angústia. And we have an argument here, it's already showing to us, that is SDF. This argument here, it's true or false. The standard for that is true. And when we run this function with SDF true, it will transform the data into a data frame. Okay? But we don't always need to obtain this data from GBIF as a data frame itself. If we are using the data for other packages, it is fine to use as data frame here, set as true. But when we are using inside caretSDM package, we can set it to false, and it will return to us a occurrence object. So it will return exactly the same object as we have here, but with more records, because this is a filtered data that I have in my directory, and OC1 here. Look, it is from GBIF, so it has the same information, Araucária Gustifolha, presence only, but the sample size is way bigger than we have in our local database. Okay, so this is how we can obtain data directly from GBIF. And I have OC, okay, I'll do this. We have another way to create an occurrences object. Actually, we have a way to improve our occurrences object, because okay, we can download data from GBIF. We have our own data in our directory. This is very common. Most studies in SDMs will download data from a major database such as GBIF, and then will use their own data to incorporate to the GBIF data in trying to include data that is not contemplated by the major database. So to group both occurrences, we can simply run here add occurrences, and we have OC1, which is the one from GBIF, and OC, which one is the occurrences we imported from our local database, and we run that, and then we have the sum of both databases. Here it is segregating between two different species, because I had this underscore, and caretSDM is interpreting that we have 2 species. So I kept that information here because I wanted you guys to know that if your species is written in different way in each of your databases, caretSDM will declare both of them as separate species. It will not group everything together, okay? Now, we'll be using for the next steps only the OC object. I will clean here just to keep our memory better. And then we can talk about the study area. Now, to build our own study area, we have 2 main ways to do that. The first one is using a vector data, a vectorized data, like the boundaries of some region or the boundaries of a buffer, and a rasterized data. Both of them we have ways to obtain only using caretSDM. It's not exactly the most brilliant way to obtain the study area, because it will depend a lot on your hypothesis, yeah. But we must remember the Venn diagram from Peterson and Soberon, which has the M component. The M component is the accessible area for the species, and because of that we included in caretSDM a function called bufferSDM. So bufferSDM receives our occurrences object from up here, and you inform a size you want this buffer to be. The size is in meters, so we can say that we want like 100 kilometers, so 100,000 meters. Okay, if we run this, it will get the occurrences and we'll build a buffer around it. So I will plot here. And here it shows a cloud, okay, with a buffer from points. We can see the occurrences. Let's see before that. Plot occurrences. Oh, see. Oh, here are the occurrences to our species. We can also see these occurrences if you have MapView installed. It can use MapView to see the occurrences, and MapView is a more I like to use MapView because it is more intuitive to look to errors or something like that. You can approach more significantly to understand where this record is, which city, which river you are obtaining. Like this agglomeration of records here, they are all in the same region. Why is that? Is because of autocorrelation, or it is an important region for the species. Okay, so I believe MapView is very useful for SDMs. Okay, so there are two ways here to see what we are doing, through plot, which here is plot occurrences, but also with MapView. Yeah. Nice. And now with the buffer we created, we can create our study area through the function SDM area. We will inform the buff that we want to create the study area, yeah. But we also need to inform, when we are using vectorized data, we need to inform the size of the cell we are using, because SDMs in general, they are performed in rasterized data, okay? So we divide the space in multiple cells, yeah, as a grid, and with this rasterized information we create our models. caretSDM has a way to perform SDMs in vectorized data, but this is more focused on river species like continental water fish, which live in rivers, and then it does not make sense to use a grid to understand distribution patterns. Yeah, but here we are working with a terrestrial species, so to divide the space in I don't know, regular ways, it's more suitable to use a grid. Okay, so we will get this buffer we obtained from occurrences, and we'll divide it in regular spaces through creating a grid. This grid will have cell size, and here of course depends on the size of your study area, the capabilities, dispersion capabilities of your species. I will put here like 10 kilometers. Araucária is a very high tree with seeds dispersed mostly by birds that can travel very far. So I'll put here like 10 kilometers in each grid cell, okay? And another information that is very important is the output CRS, of course, yeah? I am using here metrics because we like to use a metric CRS in our studies. That's because of the region we work the most, which is a subtropical region. If we get the cell size in the northernmost part, or the closest to the equator, to the tropics, they are bigger cells than the cells from next to the poles. Yeah, this is called meridian convergence. It's a geographical problem that when we use a metric CRS, we are trying to correct that. So each cell has exactly the same size in area, okay? And that is a key information here, because this solves a lot of problems regarding filtering occurrences, like calculating area. So it's a key element from our studies, okay? So we are using here 6933, which is a metric system that is adequate to our region. If you want to use a metric CRS and you don't live in South Brazil or Paraguay, Uruguay, Argentina, you'll have to search what is the best CRS for your region, okay? Here I am using 6933. And these three informations are sufficient to build our study area or SDM area object, okay? So here is the object we created. It has a class SDM area. Here is the coordinate reference system, the resolution, spatial extent, and so on, okay? We can see here that we don't have any predictors in this object. It's because the buffer doesn't have any information to be used. But there are other ways to create our study area. Yeah, we used here a buffer, which I believe is a very powerful approach because of the BAM diagram we discussed before, but we can also use a vector that we have in our folder. Okay, so let's imagine that you created a vector or downloaded a vector from, I don't know, a country, or country is not political borders are not very adequate for SDMs, but you can use like a bioregion or a ecoregion from WWF, or some polygon from IUCN. I don't know. Let's imagine that you obtain this vectorized data from another source saved in your folder, and now you can enter directly into the SDM area function. Again, our idea here is to not use other packages, so we encapsulated a lot of other packages to solve some issues. Okay, so in the same way as before here, I will just copy and paste. We have to inform the cell size and the output of our grid. Okay, and that we will see that it changes a little bit, because the vector I had in the folder is a vector from it's actually a boundary from a state from South Brazil called Paraná, and here is the grid we built within the vector. Okay, but the vector itself in my folder, it has information besides its geometry, like it was obtained from a bigger vector, which was from the whole country, and I selected just this state to have here, but some information were kept inside the vector, which are some codes there, like here is the name of this state, its code, and so on. And this information, when we enter a vectorized data into caretSDM, it is interpreted as a predictors data. Why is that? Because of what I said before, we have a way to obtain predictors data and a study area in lines, like a river vector, or instead of a polygon we have lines, or a major grid road, a network of roads, of rivers. We can obtain this information, creating a study area not based more in cells but in lines, and we can extract information from these lines through this process. That's why we have here these strange names here, that if you are using a shapefile from a database you are downloading, you are probably going to obtain this same case, and then what you need to know is that you can delete these predictors in a further step. Actually, you can do that here, but I will show you how to do that before. Okay, because we have here another way to obtain our study area, which is not more with a vector, but a rasterized data. Okay, and I will show here a rasterized data, a rasterized study area. You can skip some steps, because why we are informing here a cell size when we build a study area with a vectorized data, because we don't have a cell size. When we include a raster to build our study area, it already has a cell size information within it. So you can inform a cell size and create a new grid more coarse than the raster data you are entering. But you don't need that, okay? You don't need to do that. It can be obtained directly from the raster you are including. So I will try to run here. We have a folder that's called current inside our input data. It has a lot of rasters from WordClean, okay? And with only this information, we are able to create our study area. What is the problem here? It will get the whole raster and will build a study area. But these rasters, they are global rasters. So if I run this line as it is, it will probably crash my computer because I am running a lot of things at the same time. And this will not work. So we need to crop this information beforehand. How do we do that? We included here a crop by argument that we can inform with a vector such as the buffer we have just created. Okay. Studying SDM for so long, I believe this is the main approach most users will get. You have the rasterized data from WordClean. This is just an example, yeah. We can obtain using a function from caretSDM, WordClean data. You can take a look if you want. This function will download WordClean data to your folder, so you don't need to get from the website and put in your folder. With this function, it will do all the job to you, okay? But running this approach, I believe is the most used approach currently in SDMs. We get the environmental data, we crop it with a study area, and then we enter it into R, or then we will start our SDM approach, okay? So if we take a look at the SA object, now it has all these rasters we had saved on our folder. They are now in our SA object, okay? Because when I entered just the folder with the files, okay? We can still add new predictors if we want. It would be something like that. Add predictors, and then we need to inform the predictor. If we have like this study area had before, which is the one with the raster, with the vector data from Paraná, we can do like add predictors SA, because we are adding predictors to our study area we just created, and then we can put here like the input we put before, input data current. And let me just remind you that with this approach with the vectorized data, we have these predictors that do not mean anything, right? But we can add the predictors it will rescalonate data to match this grid we created. And now we have the 4 variables that do not mean anything and a lot of other variables that are here, okay? And then we can select, I mentioned that before, select predictors from SA, which one we want to select. Now we want these here. I'll get some 3 or 4 here, so we don't spend too much time with that, like here. There are ways to select to make that programmatically, but as this is a beginner's guide, I will not be doing that. So if we run, we want just bio 1, 10, 11, and 12, and we run that. Now the object SA has just those predictors we selected before. Okay. If we run here SDM area with a question mark, we have a lot of information. I'm doing my best to keep it very well documented, and we can see we have other functions to help with data handling. I will not go through all of them, but predictors. But you can go and take a look with what everything here does. Okay. So we have this study area which we are building using our predictors data. We have a way to add new predictors. We have a way to select the predictors we want or not to use, okay? But the study area object will have also will hold also the scenarios we are projecting our data. So how do we do that to add the scenarios? As we already did here with add predictors, we can also have a add scenarios function. What are the scenarios here? Usually when we run species distribution models in R, we are very subject to our abilities with GIS and R. Yeah. So projections, the scenarios actually, they most of the times they will only enter at the end of the workflow. But here is important to us to allow the scenarios to enter in the beginning of the process, because there are some choices the modeler can do, like transforming the variables into PCA axes, which will need the scenarios data to be changed. So within the workflow, we consider that it's more suitable to include the scenarios in the beginning of the process, okay? So we are including it here. You don't need to include it here. You can include it at the end of the process. But to avoid some errors, it seems reasonable to include it here, okay? The main problem that appears here when we are adding the scenarios is the fact that the names of variables don't match. So what happens because of that? Let's imagine that we trained a model with bio 1. The bio 1, so bioclimatic variable 1, it can be multiple, can have a lot of different names. It can have WC 2.1 underscore 10 underscore bio 1.tif. It can be like that. It can be just bio 1. It can be called bio 01, and so on and so on. There are multiple ways to write the name of a predictor. Packages do not know the difference between each of these. And as we mentioned before about the name of the species that should be exactly the same, here it's even more important. When we say that, when we are training the model, that the species has a relationship with bio1, and we model this relationship, when we will project that relationship into a geographical space, the model needs to know what is the value of bio1. If the projection do not have bio1, if it has bio01, it will consider that this predictor has value of 0 or NA, and it will bias the model, okay? So it's very important that in every step we have the same names. And I try to use some internal functions to correct this information, but I cannot guarantee that everyone will be using bioclimatic data. Sometimes we use like soil data, some hydrological data, even fire data, and it is not possible to correct that automatically, okay? So we need to correct this information. How do we do that? Using a set predictor names function. As an example here, I have we have this object SA with 19 predictor variables. Here are the names of these variables, and we can it's very difficult because we have bio1, and the second variable is not bio2, it's bio10, because it is in alphabetical order. So 10, 11, 12, 13, 19. Then comes bio2, okay? This is very important because we can set the predictors names whatever we want. But if we don't pay attention that it is in alphabetical order, this could screw all our modeling, because we can run this way and have bio1 to be bio1, bio10 to be bio10. But if we do something like bio1, then bio2, bio3, then bio4, and put that in numerical order, the package will not know that you are calling bio2, bio10, and will correct this information. So when you run your analysis, you see, oh my god, bio1 and bio4 were the most important variables for my species. That doesn't make any sense. Of course it doesn't make any sense, because bio4 actually was bio12, and when you renamed it, you said that bio12 now is called bio4, and then this could cause some errors, okay? So you have to pay attention to this information. Here I already have it in alphabetical order, so we can run, and now we see that the names of variables change to bio01, bio10, 11, 12, and so on. Okay? So this is how we change the predictor's name. For more informative names, okay? But then we have here the add scenarios. And scenarios in WordClean 2.1, they are already with a name that is different from current names. So when we look to data here in the folder, when we download data from current scenario, we have these names with a code, yeah. But when we go to the future data, we have stacks, yeah. They are raster stacks, and each of these, if we enter them, we will see that they have these exactly names that I used here. Okay. Here is it is ready to be read. Here we will use then add scenarios. Here instead of current is future, is the folder we saved our future data. Okay. Then we have two other elements that we can use. The first one is something we discussed before, which is the crop by, okay? Because these data in the future here, they are global data. And we don't want to project it to the whole globe. We want to project to a specific area. And then we can use crop by to adjust this area, okay? Here I will not be talking too much about that, but here you can have a glimpse of what a invasions assessment could look like. Yeah, you model the species using one region, and we'll project it into new scenarios using a different area. Okay, a crop by is different here. And you can also include here variable selection. There are stationary data that we can inform, like if we have a grid soil information, we can say that our predictor variable that is stationary along all the time is like cation exchange, and then this information will be exactly the same in all scenarios. Okay, it's just an example. Okay, oops, I didn't run that before. Yeah. No, it's not crop by, it's crop area. I missed it here. Sorry, guys. Now, yeah. It's important to note that here, when we built our study area, we did not inform the cell size we wanted. So it got exactly the same cell size from the raster data. With this information, we can add a new rasterized data in different resolutions that all predictors, it doesn't matter the resolution, they will be always transformed to the resolution of the study area. This is a key element to maintain resolution in every scenario, every predictor we have. Okay, so if you have different sources of predictors using different CRS, different resolution, different extent, this will always be corrected underlying these functions here. Okay, add predictors as well will help with that. You don't need to make it manually. Okay, so here we already run. we have the SDM area object. It has 19 predictors. It has some spatial extent, the resolution, CRS, and now we can see that the object has grown. We are always using our objects to inform our functions, and we will be saving that object again and again, making it grow. Okay, before we had just this information here, but now that we included the scenarios, we included a transfer data title here, which has a number of scenarios names, and we try to infer here the temporal extent. Okay, so we can plot the grid to see how it is, and we can map view the grid as well here. Okay, Paraná state there, and our data. Nice. Okay, this is what I had we had to understand about our SDM area function. And now that we have a SDM area complete and we have the occurrences area complete, we can jump to the input SDM, which is putting everything together. We just inform input SDM both occurrences and SDM area objects, and we will create a input SDM object. Okay, and we can see that it's a presence only data with Araucária angustifolia. It has these predictors, and now we have the information of the software we are using. Yeah. What else? Oh, and the transfer data. Where are we transferring our models? Yeah. Projecting. Yeah. These names, overview data, biodiversity data, transfer data, these all follow ODMAP, yeah, from Zurel. Yeah, it's a way to inform methodology in SDMs, which is a gold standard currently in the SDM literature. Okay, now we came to the very core of caretSDM. We already performed our occurrences, built our occurrences data, we built our study area, and we put those things together. Now we can perform some real analysis here, okay? It is common in SDM when we are working, we spend a lot of time in putting data together, because we say that when we enter garbage in our models, it will output garbage. So garbage in, garbage out. Yeah. So it's common to spend more time in this putting together process. Now things start to get a little quicker. Okay. One thing I missed from the previous section was to make a pre-selection of variables. Yeah, we can do that in the SA object, the study area object, but we can do in input SDM as well. But I will include here in the previous section because I believe it's more adequate, but we can do that at any time. Okay, which is the select predictors function. When we do that and we select, like I will pre-select here just some variables, so the running time from the next steps will be quicker. So I'm pre-selecting here this piece. I strongly recommend you to pre-select your predictors because there are some predictors that can cause some bias, like the quarter variables that have some problems with environmental gradients, yeah. And then we can again put together here, and now we only have 3 predictors and not the 19 predictors we had before. So from now on, functions will be more from analysis than from pre-selection and management of data. Okay, we have the first one we'll be running is a data clean function, which can be used before in the when we put occurrences together. We can run this function here. It will work with a occurrences object, and it could be useful to run this function in this step because of buffer. Yeah, if we are using a buffer SDM to create a buffer, we need the data in the buffer to be a good data. So we could use this data clean before. But as I'm using here a pre-selected data from my folder, I don't see the point of that. So now I'll run the data clean. Okay. You may see this information here. It's from another package that is very good for data cleaning, automatized data cleaning routines, which is Coordinate Cleaner. We wrapped the package here, but we also provide an argument to implement custom functions for cleaning. Okay, I will not enter in this topic because it would take a lot of time, and it's a more advanced use of the function. Okay, now that we have run the data clean routine, we can see that I saved the object in itself, so it growed a little bit. Like before we had these objects which had overview and data and so on, but now we have in data here we have a data cleaning topic that informs which transformation, which cleaning processes were made. Like as an example here, if a record is within the centroid, is the centroid of a country, it is excluded. Or if it is duplicated, we have 2 lines with exactly the same latitude and longitude, it will be deleted. Identical, if we have the same value for longitude and latitude, like -30, -30, it will be deleted. If it is terrestrial, this one is important. If you are working with maritime, like oceanic species, you should change here to false, otherwise it will exclude all your data. Okay, yeah. So here, with only one quick step, we have already implemented this data cleaning process, and now we have only 100 records. Yeah, we can plot. I'll actually map view. We can map view our occurrences to see how they changed. If you remembered from the other section, we had a lot of records here in this region, which is the capital of this state, and now it is more sparse. Yeah, very nice. Okay, this is Curitiba. It's the region. We have a lot of Araucárias here actually, but we also have a lot of institutions that work with Araucária, and then we have a lot of records here, but it's just autocorrelation, yeah, spatial autocorrelation. We can even see that there is a city here called Araucária. Yeah. It's a very important tree in the region. Now we perform our data cleaning. Then the next step would be to run a multicollinearity assessment of predictor variables, and then we have this function that is multicollinearity SDM. We inform, as always, the input SDM object. We will always do that, and at the end I can talk a little bit about why this is important. But we will have also 3 different methods for those who use USDM package. There are 2 methods from USDM, which is VifCore and VifStep. I like to use VifCore. I'm very strict in my multicollinearity assessments. I always like to use like a 0.5 threshold, so all predictor variables have less than 0.5 Pearson correlation, yeah, which is very, very, very low, I know, but I think in this way we can have a more robust assessment. I don't know, we can one can argue that. But we also have here a PCA approach, yeah, where we transform the predictors and scenarios data to PCA axis. In this case, it doesn't make sense to make this selection of predictors, yeah. It makes more sense to have more predictor variables to use a PCA here. So I'll be using here a VifCore approach from NAPI-EC. And now we can see that the object will grow, yeah. This is the idea. We will keep track through the whole process by always informing our object with new information. So here, where it is, let's see. Oh, here, model, multicollinearity, variable selection method, VIF, and selected variables, bio1, bio4. Oh my god, even that. I will raise here the value, so we can have at least three selected variables to model species. Okay, now the next step would be to retrieve pseudoabsences, and here it's a key difference from this package from others. Is that we have pseudoabsence, but we also have background data. So what is the difference between pseudoabsence and background? It's a very long discussion. I can include a reference in the description of this video if you want to understand a little bit. But most of the packages don't have different functions for those things. They all rely on the same function to perform both, to obtain both, even pseudoabsence or background. Like the SDM package, I believe it's the function is called background. So if you are using pseudoabsence, you have to use the function background to obtain pseudoabsences. And the package biomod 2, I believe it only uses pseudoabsences. And if you want to use background data, then you have to use the pseudoabsence function to obtain the background data. So to avoid this confusion, we segregated both. If you are using like Maxent, which is probably what most people do, like 90 to 95% of literature published in SDMs is using Maxent. You would use then the background function. In our works, we like the most the pseudoabsence algorithms because we are more prone to this machine learning analysis, and we work with that. Well, you can see in the other videos in this channel that we built ChooseGCM, which is very machine learning driven. Yeah. So pseudoabsences here we have some pre-included ways to obtain pseudoabsences. We have a random approach, which I believe should not be used never. But we have also BioClim, which builds a surface range envelope around the environmental space using the records of the species. It's a presence-only method, yeah? Oh yeah, here. It's a presence-only method to model species distribution. We can also have this same presence-only approach using Mahalanobis distance. We have a geographic approach, which is the buffer SDM, and it works exactly as the buffer we created above. But it can also be a custom function. So if you like to build your own function to test some hypotheses regarding pseudoabsence selection, you can create your own function and include here, and it will work as well. Okay. We have some information here on how many sets of pseudoabsence you want to obtain, and we have the number of pseudoabsence you want to obtain. A very common misconception when people confuse pseudoabsences with background data is to put like 10,000 pseudoabsences to inform models. Our standard approach here is no, which avoids imbalance problems obtaining the same number of records and pseudoabsences. So if our species has 100 records, it will obtain 100 pseudoabsences. If we had an object here, we just have Araucária angustifolia, but we could have in the same object here multiple species. So if we had Araucária with 100 records and Ilex paraguariensis with 82 records, the pseudoabsences function would obtain 100 records for Araucária and 82 records for Ilex paraguariensis. Okay? Okay. And here we have an argument that helps a lot with BioClim and Mahalanobis distance, these environmental ways to perform pseudoabsence selection. Because if we had our 19 bioclimatic variables, we could use not the whole set of predictor variables to build these envelopes. Okay, we could use like, I just want the bio1, which is mean temperature, and bio12, which is the annual precipitation. Yeah, so I will use just those two variables to build the envelope in which outside this envelope we will obtain pseudoabsence. So in this way we have pseudoabsences that are more similar to real absences, considering at least the environmental constraint here. Yeah, so it's another way to make it. Okay, now we retrieved our oh my god, we retrieved our pseudoabsences. What will happen with our input SDM object? It will grow, it will change. Look, now we have that observation type is presence absence, pseudoabsence. Before we had presence only, right? Now we have this information that it has a pseudoabsence selection within it. And here we have the method we use to obtain the pseudoabsence. We have the number of sets and the number of pseudoabsence per set. Yeah? And we have here also the PA to presence ratio, which if we use nu as the number of PAs, it will always be 1. Yeah? Because it's exactly the same. Now, we have already cleaned our data, obtained both occurrences and predictors, put that together. We managed to filter predictors and occurrences to represent better our species. We obtained a negative class here with our pseudoabsences. Now we are ready to run our models. Yeah, and we have then the train SDM function, in which we will have the object I always, the algorithms we want to use, we have a control argument, and the variables we want to use with our in our models to model our species. Okay, here I didn't mention before, we could have like bio 1, bio 12, but we can also inform a method that we applied multicollinearity in our data. So if here we use it, you could use a custom function here, and this function would call like I don't know, my method. Yeah, this would be informed in our object, and you could use here in variable selected my method. You could use in train SDM my method. Yeah, to select the species the variables the way you want. So train SDM here is where caret came from. Caret is a package in R that is huge. It is aimed to run machine learning methods. It's not what I want. It is aimed to run machine learning methods in R. Okay, so it's a very big package. It's very important to machine learning culture in R. And it has this function which is train. It encapsulates a lot of different arguments and a lot of different methods. We can see here that only in train we have a lot of different tuning parameters, the control we had, pre-processing of data, the algorithms, and so on and so on. Everything that you see here in train or in train control can be passed to this function. Okay, we have here the train control, and we have the train, yeah, which works exactly the same as in the caret package. Here we have informations like the algorithms we want to use. So we have this object in the package that is called algorithms. If you run here, it is a giant table with the names of the algorithms and informations regarding each one of them, how they work. Like these are generalized linear models, 0 no, 1 yes. Okay, so you can filter which types of models you want, like tree based here, two class only, and so on. Okay, now there are, let's see, 117 at least algorithms in this package. We implemented also Maxent, which is not here, and Mahalanobis distance and a bioclim, so envelope. So there are a little more than 120 at least, okay, algorithms. But of course you never want to run all those algorithms at once. This would be very heavy to run. What I do usually in my studies is to select one algorithm from each kind of algorithm family. Yeah. So my usual selection involves these 6 algorithms, like random forest, GLMNet, which is like a regression. Random forest is a tree based, MDA, which is a analysis discriminant, SVM radial, which is a support vector machine, and NET, which is a neural network, and Navy base, which is a based algorithm. We could also use here a KNN, which is a nearest neighbor. So there are here like 1, 2, 3, 4, 5, 6, 7 different types of algorithms. Each type of algorithm is contemplated here. So if a neural network is able to understand some pattern from the data that the others cannot understand, it is contemplated here. And the problem of using too much of the same type is exactly that. If you only use tree-based algorithms, you could be pruning your model since they can miss some information in the data that tree-based algorithms will not be able to infer. Okay, so I like this approach. You can dig deep into that helm. It is very huge, and I will not be going any further here. Okay, so I selected here just 2 algorithms so we can run quickly. We have here the train control, which will control the validation in during the training. So we have the method, which I like to use repeated cross validation, the number of folds, which I'm using here for how many times we will repeat this cross validation. Here it should just to make it quicker. If it was a real study, I will put probably here 10 and here at least 10 as well. Okay. These parameters you must always inform, which is the class probabilities. This is what we want to obtain. Occurrence probability, yeah. And the summary function, which we built and we deliver together with the package. This summary SDM, it's a function that caret uses to calculate metrics. So if you just run the standard approach from caret, it will not calculate some metrics that we'll like to use a lot in SDM studies such as kappa as an example, or TSS and ROC. I believe it will be calculated, but there are some other metrics that we use that caret does not standardly calculate, so we provided this summary function. Okay, so I will run here, and while this runs, I will put here that we can see. Okay, it grew a little bit. Yeah, now we have some more information regarding which predictors were used to build the models hyperparameters. This is a key difference from caretSDM. It is able to build different hyperparameters in an automatized way. Okay, so most packages you need to inform which parameters you want to fine-tune, and here all algorithms you run will be fine-tuned, because they already have mapped which are the hyperparameters, what is the type of data it goes in, so you don't need to inform that. You can inform, however, the size of the tune length you want to implement. So you can put like 100 here, and we will have 100 combinations of different hyperparameters to each of the algorithms. Okay, I didn't mention here before, but you can also inform a custom function as your algorithm. You can inform custom metrics to be obtained. A lot of different methods we have here, functions. They are all customizable. Yeah, you can build your own function and include that. Here we have run here the algorithms. Okay, and then we have the assessment here, which is the cross-validation metrics. Yeah, how well our models performed. Yeah? And we have that KNN and Navy base, both were very similar with ROC, TSS, sensitivity, specificity, but we can get this function, which is mean validation matrix, and show to each of these pieces the validation metrics to each of the algorithms and to everything we have calculated here, like the true negatives, the CBI, kappa, and so on. Okay, we can see, however, not just the mean but the whole set here. We have the metrics to each of the pseudoabsence components. Yeah, can obtain that as well. Now, with our models, we can then predict it finally to our scenarios. And here we have the object I always in the beginning, and then we have the metric that we want to filter our models, and the threshold we want to apply to this metric. It can also be a custom function. So if we want, like, instead of the AUC, we can run like the TSS to be higher than 0.7. Then what the function understands is that we will only predict models with TSS higher than 0.7. Okay, here I use an AUC of 0.9, which is all models. Okay, and the object growed a little bit with now the predictions layers, and the unit, which is occurrence probability. Yeah, when we perform this classification analysis using machine learning models, we are obtaining the probability of a class, the presence probability. Yeah, as we have a counterpart, which is the pseudoabsence, then we call that the occurrence probability. Okay, and now we have our predictions. We can pass to the ensemble of predictions, which of course can have custom functions, but we will usually have a standard method such as the average, the committee average, or a weighted average. Yeah, the weighted average, we have different arguments to say which metric we want. If it's the committee average, which method we will use to binarize data. Usually we have TSS, the maximum sensitivity and specificity to binarize the models, the projections, and so on. Here I will just only run an average, which is quicker, and this video is very long as well. So we already have here the ensemble method, which is average. Okay. One final thing caretSDM is able to do is to group GCMs. Whenever we are projecting data to the future, we have the general circulation models, which in these files from future here in our folder, they are coded in the first two letters. CA here is one GCM, MI is another GCM. So we can ensemble the GCMs informing exactly that. So CA or MI are the ensembles, the GCMs, and they will be used as a key element to search through the scenarios to say, or CA and CA, they are different scenarios. So we cannot group these things together. But this one and this one, they are the same scenario. So we need to group these. That's what we are informing here. Okay, so we run that, and now we have the ensemble names here, and we can finally plot our ensembles. Plot or map view the ensembles. Yeah, we use plot ensembles for that. We can see for the current scenario, the occurrence probability, ensemble types the average, and the Araucária language folha distribution. We can plot that for a medium scenario, climate change scenario, and a more harsh climate change scenario. This species is very related to cold temperatures, and this region it's higher than the surroundings, so it is expected for that to go into this region which is higher. Yeah, and this region here is even higher. Okay, so is that is caretSDM. Some final functions I wanted to show you guys is PDP-SDM, which is the partial dependence plot, which shows how the species relate with each variable. So we have the probability of occurrence versus variables. Yeah, they are very fine here. The response curves. Yeah, we call that response curves in machine learning literature, we call it partial dependence plot. Yeah, that's why it's PDP-SDM. We have also the variable importance here, which is the analysis. We can enter there to read a little bit about and how to obtain this info. And we have another function for those who like to use GIS packages in R. You can transform the results using a function like SDM as Terra, or SDM as Raster, or SDM as stars, and so on. But you can also, if you like to use a GIS software such as QGIS, you can use the write ensemble function, write ensembles, which will save your ensembles in the folder. And you have a lot of different functions with write, like write predictions. You can write the models, you can write the grid, the validation metrics, the pseudoabsences, occurrences, everything to make it available to be entered in a GIS software, if is it the case. Okay, so this is caretSDM. As I showed you, it is majorly composed of only one package from the beginning to the end. This is maybe the only step where we are using another package that is not caretSDM. But of course, for a experienced modeler, it has a lot of different forms, different ways to customize functions and apply your own ideas, given this closed framework that you can run from the beginning to the end. Yeah. To finish, the third finish, I think. To finish, I just want to show you the package website. Yeah, we have this website which informs that here how to obtain help, how to install, but also it has a lot of articles here that I wrote, and they inform how to use the package in different ways. So the first thing here is the concatenate functions in caretSDM that shows how we can use pipes to concatenate one function into the another, and this makes our script more compact, more easy to read, and I'm really proud of this achievement here, because I think it's really useful for most people, even more for beginners, which is the reading of the script becomes more easily. Yeah, and then we have other articles here, like how to add new algorithms to caretSDM, how to perform species distribution modeling. Here is this article here is what I used as a guide to build this video. Yeah, obtaining here partial dependence plot, the projections. Yeah, but we also have, as I mentioned, the opportunity to use lines as components here for the study, and not grid. Yeah, so here it's an example on how to project species distributions using vectorized data, not rasterized data. Yeah, this is for a salminus species, a fish species from Paraná as well. So the same idea. Yeah, and we have other things like ensemble of small models for rare species, projecting non-native distribution, which is for invasive assessments, how to use Maxent in caretSDM. I believe most people like Maxent and like to use it, so here is how to use Maxent, and how to not use, like I show how to obtain some errors and how to solve those errors, yeah, that could appear. And we have some benchmarks here comparing our package to other packages, the processing time, which is very quickly for us. Here I have some pseudoabsence selection. Here I show how to create your own function to obtain pseudoabsences, and a little bit about hyperparameter tuning at the end. Okay, so if you had any doubts, if you had ideas on what we could improve, you can always email me and send some message. I am very open to collaboration, and I think SDM community is a very approachable place, despite the literature sometimes is very confusing because of some errors that are perpetrated. I believe to learn with other modelers is easier, and this video is to help you guys use this package, which I put a lot of effort in it, and I expect you guys to like it. Okay, that's it. A very long video, but I believe very useful as well. I expect you guys liked it. Bye bye, and see you in the next one.